Now it's very good. Okay. All right. Yeah. So good afternoon, everyone. Really a great pleasure to be here. It's my first trip to India, and so I jumped at the opportunity both to come and also to be here as part of this festive occasion. The Gang of Four paper is one of my very favorite papers, and when I get to that point in my condensed matter class, always have a good time telling the students about it. So it's wonderful to be here and to be part of it. I'm going to tell you today about applications of a new technique that I think will be very powerful for many problems that we're interested in a wide swath of modern condensed matter physics. I think it's fair to say that, and this was kind of alluded to in Piers's talk earlier today, that we're for many things that we're interested now in modern condensed matter physics, they're kind of quantum correlations, to put it broadly, that we don't necessarily have the tools to measure properly. We think they're important to the physics, but they need to be better characterized. And so I'm very bullish on the idea that we need to find new ways of measuring things, and if you will, kind of a next generation of, particularly when it comes to spectroscopic techniques. So I'll be telling you about our development and use of a new technique, which is called terahertz two-dimensional coherent spectroscopy. It's a pump probe technique. It's, if you will, like pulsed nuclear magnetic resonance, but with terahertz photons instead of radio frequency photons. It could go by different names, and indeed we haven't invented it. Techniques like this are well known in the nonlinear optics community and go by the terminology of things like four-wave mixing. In other contexts, it's similar to what we know as photon echo. The 2D refers to two frequency dimensions, and so I'll tell you about the technique and our applications of it. Unlike most nonlinear techniques, it is low energy. So it's the terahertz part of the electromagnetic spectrum. And I think that's important. So, as I'll allude to, nonlinear optics, it's not a new field. It's a very old field, in fact. But applications, nonlinear optics in the terahertz range is reasonably new. And that's, of course, when we're thinking about trying to understand the cooperative behavior of solids at low temperatures, we want to think about coupling to it at low energies. So, the few millieV scale, which corresponds, let's say, at most to tens of Kelvin degree scale. And that's what we're doing in a technique like this. Before I get into all of that, let me thank the various people who made this work possible. People like my former postdoc, Kota Katsumi, who is now assistant professor at NYU, various students and other students and postdocs. In particular, I'm going to concentrate mostly on the work we've done on correlated metals. And so I want to point out the work of my former student, Deepajan Chaudhuri, who is now at the University of Illinois, and originally led the work on the cuprate superconductor work that I'll tell you about, and current student, Will Young, who's working on this project now, and kind of many people that I've been fortunate to collaborate with, various theorists, Rahul, who will give the talk right after mine, and various people who I've been fortunate to collaborate with on sample growth over the years. And in particular, I want to thank Ivan Bozovic, who have a longstanding collaboration on cuprate superconductors. So one of the things that I want to understand today in the context of quantum correlations in solids is, for instance, the linear, what we heard earlier, called the so-called Planckian resistivity in the cuprates. And this is a notable behavior of the first found in the resistivity versus temperature, which is almost perfectly linear over an incredibly large temperature range, almost to the melting temperature of lanthanum strontium copper oxide. And we can always cook up some model that will give us linear in T resistivity over possibly some limited range. But what's difficult to understand is how you could get linear in T over such a really large range, right? If you will, there are different kind of mechanisms or microscopic models might give you linear in T over some range, but what we really want to understand is how does the system know, if you will, how to pass the baton smoothly from regime to regime, all the while keeping the same linear slope. When we measure this in optical conductivity, so I'll show you further data like this later on, this is measured with terahertz spectroscopy, the conductivity as a function of frequency, and this is a linear conductivity experiment. So it's not nonlinear conductivity, it's linear conductivity. And this is near slightly overdoped lanthanum strontium copper oxide, and this is what we might call the Drude conductivity peak. It's the conductivity as a function of frequency, it's the real part, And as you get closer down to lower temperatures, this peak gets sharper and sharper. And we plot here the width of this peak as a function of temperature. And it has this kind of notable linear in temperature behavior, which corresponds, this is over a limited temperature range, but corresponds very closely to this linear in temperature range there. Okay. The technique I will tell you about is a nonlinear technique, and optical nonlinearity is, of course, is an old subject. When we think about driving some particular physical system with, say, an electric field, the linear response is the response that we usually think about in terms of the optical response. We like linear response. It's simple and it's powerful, but all physical systems have nonlinearities. Nonlinearities are frequently a source of complication, but they can also be an interesting source of phenomena, and they can be an interesting source of information for us. There are different kinds of nonlinear response, and they go by various names. One can think about things like the second harmonic generation, where 2 photons come in and 1 goes out. There can be third harmonic generation, 3 photons coming in, 1 come out. And then various versions of this where, let's say, a positive frequency counts for one, say, omega of a positive frequency, negative frequency, and then emitting a third photon, again, bringing you back down to the ground state. The particular response I'll tell you most about today, and one that's quite generic, is this one here, which we call 4-wave mixing, which will be the same one that we're talking about. We'll be thinking about using positive frequencies and negative frequencies, if you will, measuring, if you will, driving the system with 2 positive frequencies and 1 negative one, and then looking for the photons that are emitted. One of the things that you want to keep in mind when you're thinking about nonlinear response is we have to have a slightly different language when thinking about light matter interaction than we do typically when we think about photons interacting with materials with linear response. When we talk about linear response, very often we'll use language like we had photons at the source and the photons went to the detector and the photons were absorbed in the material between. That kind of language is not particularly useful when we think about nonlinear response. What we want to think about is that we have some driving field, it drives charges. Those oscillating charges are now a new source of radiation. And that new source of radiation, we can detect it in the detector in this fashion. Of course, there's a way of thinking about the linear response in the same fashion, but that's the picture we're going to have to think about when we think about the nonlinear response. Okay. Let me give you my conclusions in advance because I'll eventually come close to running out of time. The things that I want to tell you about today are, one, this technique of 2D coherent terared spectroscopy, and I hope to convince you that it's a powerful new nonlinear technique for looking at all kinds of different materials, spin systems with fractionalization, electronic glasses, collective mode superconductors. And I'm going to spend most of the time today telling you about nonlinearities in interacting metals and what's the particular new kinds of information we can get from doing these nonlinear experiments on systems with Fermi surfaces. And I'll give a few different examples of those. Okay, first let me tell you about terahertz 2D coherent spectroscopy. So I want to give you a simple cartoon of what the kind of thing we're doing. So imagine we have some system which is composed, let's say, of 2 weakly nonlinear oscillators. We can imagine them as kind of charged pendula. And in keeping with what I told you about how we want to think about light matter interaction, we're going to think about driving the system with, say, 2 pulses, and we'll call them A and B. And then we'll do an experiment with just A and just B, and then we're going to look at the difference. And so the difference, if the system was purely harmonic, it wouldn't matter if I came in with both pulses at the same time or 1 pulse and then the other pulse. And so this residual here, some detected electric field, that's the nonlinear signal. And so if I have these 2 weakly nonlinear oscillators and I imagine plotting pump frequency and a probe frequency, again, roughly speaking, frequencies from the pulses of A and B, I can think of the linear response of the system very roughly as thinking of it as the projection of these 2 places where I might find the nonlinear response. Here in this kind of cartoon schematic, I plotted the nonlinear response out of the board. And the linear response would be, roughly speaking, the projection of these guys onto the probe frequency axis, right? So a property of a nonlinear oscillator is if I pump it at some frequency and then I probe it at that frequency at some later time, if I pumped it at the right frequency, I can tell later when I come in and probe it what frequency I had previously, either I pumped it on resonance or I hadn't, right? Now, that would be the situation if these were 2 independent oscillators. Now imagine a situation where I couple them very weakly. Now what happens to the linear response? Well, in the linear response, if I couple them very roughly, I could imagine that the frequencies would shift, maybe the oscillators broaden, maybe they become slightly asymmetric. If I had a good enough theory, then I could come up with some story for that, but I seldom have good enough theory. But in the nonlinear response, it's not a matter of having good enough theory. I just get new peaks where I didn't have them before. And it's almost as simple as I can go in and I can shake the red oscillator and I can make the green one move, right? So it's a very, very different situation. I could also imagine a situation, maybe I have many oscillators in the sense that there are many, again, weakly nonlinear and weakly non-interacting oscillators. The linear response could just be this kind of broad blob here. Those oscillators could be very long-lived, but I wouldn't be able to tell them because the frequency axis is completely congested. But I would get this kind of streak along the diagonal, and then an anti-diagonal cut in that direction could reveal the inverse lifetime. So those are the kinds of things that we're going to want to do, we are going to do. Right? So that's what one of the experiments looks like. I'm going to tell you about the details of this. I'm happy to. I'll just say there's an ultra-fast laser. The laser comes out, goes through a variety of different beam splitters, eventually the essential parts are here. It goes to 2 nonlinear crystals. The laser is turned into a terahertz pulse. These are what the data looks like here. So these pulses are about a picosecond long. Inverse of a picosecond is a terahertz. And so in those pulses has all this Fourier content that we're interested in. And so we do experiments where we're driving these pulses, we're driving the system, and as we do it, we kind of slide these pulses through each other in this fashion. Okay? So that's what data, again, looks like. That's what, kind of a slice is, but this is the kind of experiments that we do. We do an experiment just with A, just with B. These are 2 different time directions, A and B together, and then we look at the difference, and that's the nonlinear response. Okay? Good. So what can we study? Lots of things. Magnons, and I'll give you some various examples of that. Magnets, I'll give you some examples of that. My first ideas about what we might be able to do with this system were in spin systems with fractionalization. We've done recent work on collective modes and superconductors, various kinds of nonlinear lattice dynamics, electronic glasses, which was our first experimental foray into this, with using this technique, and correlated metals. So before I get into the main part of the talk, let me give you some of these quick examples. So one of the things that we've used this technique for recently is trying to look for evidence of collective modes in superconductors. And so this was in a collaboration with Pratap Rajahuri at the Tata Institute. Now, one of the things that is emblematic of a nonlinear response is that they're given, say, a particular ground state and an excited state. We can do different kinds of pulse sequences. They're different processes, if you will, which allow us to go from some ground state to excited state. Now, if I have a linear response style experiment, there's basically just one way to excite the system. But in nonlinear responses, I can do experiments, for instance, where I excite the system, I can de-excite the system, I let it time evolve in between, and then I can excite it again, and then I can watch the system decay. I might excite it again, and then de-excite it, and then watch it decay. All of these, the chemists would call these Louisville pathways. And as far as we're concerned, each of these different processes gives us different ways of interrogating the system, and we can get different information out about it. It all sounds complicated, and it is. One of the advantages of the 2D technique, 2D, again, refers to 2 frequency directions, 2 frequency dimensions, is that these different processes appear at different places in this 2-dimensional map. The 2-dimensional map is really a 2-dimensional spectra. And these different places in this 2D map go by different names. And so this particular one here, where we're using 2 pulses, but it's a chi-3 response, so I need 3 electric fields to feature in it. And so I either use 1 electric field from the first pulse, and 2 from the second, or 2 from the first and 1 from the second. And so this particular response here, which appears at that point, turns out to be very important for a lot of the experiments we do. We call this the rephasing contribution. And if you're familiar with the idea of, say, photon echo or spin echo, it's analogous to that. Okay, so you may be familiar, let's say, in the context of NMR, the idea of the Hahn echo. So this is in nonlinear optics, this is a Hahn echo. Okay? I won't get into the details of this, but we've used this a lot on superconducting systems like niobium nitride, to look at the collective mode in particular, the so-called amplitude mode, which in some contexts people refer to as the Higgs mode of the superconductor. Famously, in a superconductor, there are at least two collective modes, and one is the possible phase degrees of freedom, which correspond to the phase winding around the minima here of the so-called Mexican hat potential, but there are also oscillations along the radial direction, and those are the amplitude oscillations. The amplitude mode in a superconductor is a scalar mode. You can't couple to it in the level of linear response theory, but you can couple to it in nonlinear response. And so we've used this in a series of papers, of which one of them is plotted right here by my former postdoc, Bhattacharjee. And you can see very, very dramatic. One, you see very, very sharp responses and very, very dramatic enhancements when the driving frequency we have passes the frequency of where the amplitude mode basically comes into the measurement window. And so I won't go into the details of it. I'm just kind of try to give you a feeling for the kinds of things that we're doing. The other thing I wanted to say is there are a variety of different responses. One of the other responses would be, say, one power, positive power of the pump field, a negative power of the pump field, and then a positive power of the driving field of the probe field. And that's a response that we call the pump probe response. And it'll be particularly important when we're talking about correlated metals. All of the nonlinear responses are here, and we're thinking about the chi3 susceptibilities, but there are chi2 susceptibilities that one can see as well. Okay. The first idea that I had about what to do with this technique was in the context of looking at fractionalized systems with possible fractionalization, quantum spin liquids and the like. If you will, we know the answer in one dimension. And so I spent some number of years talking to various people about this idea, and finally talked Yuan Wan, who's at the Institute of Physics in Beijing, who's a former student of my colleague Oleg Chernyshov, into doing some calculations with me, where we considered the simplest model system for fractionalization, which is the Ising chain in transverse field. And so if I, say, come in with a photon or a neutron, and I flip a spin in the Ising chain, I get, if you will, I flip a spin, and the elementary excitations of the system are these domain walls, which propagate apart from each other, which gives us a broad continuum behavior. Again, each of those oscillators might be very well defined. Each of those resonances might be very well defined, but you can't see it in the linear response because they're all on top of each other. But in the 2D response, you can. And so we did a series of calculations that were associated with this. This is the linear response here. This kind of broad shape is an ensemble of many different possible excitations that correspond to making two of these domain walls traveling apart from each other. There's no particular sharp spectroscopic information that can be extracted from that, again, because the excited state is a two-particle continua. But along and here in the fourth quadrant, you see this kind of sharp streak, which is this sheet of delta functions. And again, just like I told you about the pendula, an anti-diagonal cut in this direction would reveal their lifetime. So we did a series of calculations, both for kind of by an ad hoc fashion, putting in lifetimes and doing a calculation with disorder. If you put in lifetimes, you see that there's kind of broadening here, as you might expect. If you put in disorder, there's no broadening at all. The linear response is basically indistinguishable from each other. And the point we made is that you can tell the difference between spin-on decay and interactions versus disorder. You can't tell it all in the linear response, but you can tell in the nonlinear response. The first experiments that we did, and this was done in collaboration with Rahul, was on one of my old favorites, phosphorus doped silicon on the insulating side of the metal insulator transition. And again, I won't tell you about the details of this too much, but here we think about an ensemble of localized charges, say phosphorus, doped into a crystalline background, but in such a fashion that those charges are random in space. They have a long-range Coulomb interaction with each other. This system is insulating, and at some level it's strongly interacting because there's a 1/r Coulomb interaction with every charge, with every other charge in the system. There's a way of understanding this in terms of emergent dipole degrees of freedom, and this was one of the reasons that we were interested in looking at that. We know what to do with a two-level system like that in terms of modeling its nonlinear response. One of the things that we found was that we could measure the lifetime of these excitations versus frequency, and found that their lifetimes were linear in frequency with a coefficient very close to 1. And I always found one of these early papers of Phil Anderson on the disordered Fermi glasses very inspiring. And this idea of some universal state of matter of disordered fermions called a Fermi glass, we made kind of homage to that original idea. The linear in frequency dependence with a coefficient close to 1 is very close, very similar to various things that have been discussed in the context of marginal Fermi liquid. So we called this state of matter the marginal Fermi glass, and was able to learn about that, again, through doing 2D coherent spectroscopy. Okay, so those are kind of some of the things that we were doing. What I want to spend the rest of the time telling you about now is about various kinds of relaxation effects in correlated metals. So let me start by telling you something first you know, and then I'll tell you about things that presumably you don't know. So when we think about doing optical conductivity experiment, we think about, have a system like a Fermi surface, and we subject the metal to some kind of time-varying electric field. We can think about what would be a time domain version of that. So we could imagine taking this Fermi surface and perturbing it sideways. Some image like this appears in most people's first condensed matter physics class. Maybe this is how it's done in Cattell. And you think about perturbing the Fermi surface sideways, and you fill in those states and you deplete those states. And to kind of use the language we're going to use later on, we'll consider this a p-wave deformation of the Fermi surface. This is a state of finite momentum, and a time domain optical conductivity experiment would be where we've displaced the Fermi surface sideways, and then we watch it relax in time, back to the state of zero momentum. And so really what is being relaxing in this situation is momentum. The only processes which allow that state to relax are processes which take momentum from the electron system. So this is an important point, and it'll have a particular relaxation time that we could associate with it. It's the momentum, the rate of momentum relaxation of the electron distribution. We could also call it, and that's the language we use in our papers, the E1U relaxation time, because it's looks like this p-wave deformation, if you will, to the Fermi surface. So this is presumably something you know already, or at least can recognize. This is what we measure in an optical conductivity experiment. So we measure this width here, which if the Fermi surface is sufficiently isotropic, the width is literally the rate that current dissipates in the system. But if the system is sufficiently isotropic, it's the same rate that momentum dissipates in the system. Okay, so what happens now if we would use, let's say, multiple pulses to not just displace the Fermi surface sideways, but we can imagine distorting the Fermi surface in different fashion. So it's kind of, again, a cartoon of what I imagine doing. You can kind of imagine coming in with the Fermi surface and jiggling it back and forth, if you will, and leaving the charges high here and high there, but doing nothing here and there, right? So that has the perturbation of the Fermi surface. In the first case, the p-wave case, the perturbation of the Fermi surface went like e cosine theta, but this goes like e cosine theta squared. And of course, I can decompose it like this, and there's a S-wave part, and there's a D-wave part, and the S-wave part is associated with exciting everywhere around the Fermi surface, and the D-wave part is associated with, let's say, exciting it here and exciting it there, but de-exciting it here and there. And I've represented that graphically here. Again, you could imagine taking the Fermi surface, if you will, and exciting it here and exciting it there, and I can write that as a superposition of this one, which is an A1G deformation, where I've, if you will, gone around and excited everywhere around the Fermi surface, superimposed with this one, which we would call the B1G. And by this, I want you just to kind of add up plus signs and minus signs, and you'll see that you can take that plus that and get that. Now, this is a state of finite energy, right, where we've gone and excited everywhere around the Fermi energy. And for it to relax, the only things that will relax it are ones that take energy out of the electronic system. Let's say scattering events which just reorganize the electron distribution function, Umklapp scattering, if you will, or electrons scattering off impurities. This doesn't do anything to relax energy. One would expect that they will relax at different rates, and because the conservation processes are different for both. Okay, Now, so this is where we're going with this, is that through kind of comparing these different channels, in particular watching how do the different channels decay, we can isolate different kinds of scatterings. And so what I'm going to spend most of the time telling you about is the A1G channel, which is easy for us to see. We're still working on seeing this B1G channel, which is interesting for many regions, but it's very fast decaying. There's no conservation law that's associated with it. It's at least at lowest order, neither a state of, it's not a state of finite momentum, and at lowest order, it's not a state of finite energy. It decays very quickly, and it's been very hard for us to see. I think it's there for various reasons. But we get a lot of information out from the channel that's easiest for us to see, and that's this A1G channel. The A1G channel is, in the conventional picture, only decays via electrons scattering off of acoustic phonons. So that's the only thing at low energies which will take energy out of the electronic system. Now, what do we know about that? So let's take a simple case of electrons coupling to phonons. We can compare the momentum relaxation rate and the energy relaxation rate. So the momentum relaxation rate is, at least in the textbooks, would tell us electrons scattering off of phonons goes like T to the 5th at some low temperature. And then at some temperature, which is of order some fraction of the Debye temperature, goes linear in temperature with actually a coefficient very close to 1. And that's important for some of our discussion, which will come in a bit. This regime up here we would call the elastic phonon regime. And it basically comes and when the electrons involved are thermally excited with enough energy that they have energy that's a lot larger than the characteristic phonon energy. And so it looks basically like, if you will, just elastic scattering or impurity scattering off of impurities because, again, the electrons have so much more energy. The energy relaxation in the same scheme is quite interesting. At the lowest temperatures, it would go like T to the 3rd. And then there's a peak at the same temperature where we go to linear in T. And then it's actually a decrease in the elastic phonon regime. And that's just perhaps for the obvious reason that when you go to high enough temperatures, the electrons, again, have a lot of energy. They have a lot more energy than the phonons do because they're limited in energy to the Debye temperature. And the phonons are very inefficient to take away energy out of the electronic system. This was first worked out by Phil Allen in 1987. It is, I think that it's been used quite a bit for various kinds of optical pump experiments. And I'm not sure that it's really applicable to that case. Although there's been a lot of work done where you're pumping the system with 1.5 eV photons in a 1.5 eV laser. When you do that, you make this very, very high energy electron hole pair. And the assumption is that there's this kind of fast decay back down to some very low energy scale. But I think that's an assumption which is not particularly justified. I think Allen's theory basically applies just directly to the kind of experiment we're doing, however. Oh, and then this T to the 3rd, the lowest temperatures, is very, very close to the contribution of the electronic self-energy from the electron-phonon interaction here. So at low energies, at low temperatures, you expect that this energy relaxation rate tracks the contribution of the quasiparticle self-energy from phonons. Okay, so what does this actually show in interacting metal like cuprates? So I'm going to tell you about cuprates here. We've worked on a variety of other systems. If I still have time, I'll tell you a little about strontium tightening. So we've done a variety of different experiments, and this gives you some kind of feeling for what they show at the kind of largest and grossest scale. So we can do, I've been telling you a lot about these sophisticated terahertz, this two-dimensional coherent spectroscopy, but we can do lots of different experiments with these intense terahertz pulses. And this is kind of the simplest one you can imagine, where we measure the transmission through the system as a function of the applied electric field. And so if I was purely in a linear response regime, it wouldn't matter how hard I drive it. And so this provides a way of getting a reasonably accurate but kind of frequency average version of trying to get the nonlinear coefficient that comes out. When you go and you do this, when you do this analysis on the cuprates in the normal state, you get this number here, which turns out to be the largest nonlinear susceptibility in the Chi3 susceptibility has been ever measured. I mean, it's orders and orders of magnitude larger than in the normal optical range where nonlinear optics is usually performed. Previously, the largest nonlinear susceptibility was in graphene, but this is now if you will, superseded by the cuprates. That is, I can't see it very well. What's that? It's 10 to the -9, yeah. So I have the wrong glasses on. I can't see it very well. So yeah, so a normal metal with parabolic bands and elastic scattering has no nonlinearities. So there's essentially two ways that a metal can be nonlinear at low frequencies. It can be have very non-parabolic bands. And so that's like the case of graphene. And graphene was previously the largest nonlinearity that anybody knew. Or it can have very large inelastic scattering, or if you will, energy-dependent scattering. And so cuprates, of course, have very large inelastic scattering. And this is what we think is going on in the system here. And Avishkar and Subir Sachdev have a paper on this. What's that? It's frequency dependence. This, as I've done it here, is kind of a frequency as a frequency average value. It's not particularly frequency dependent. Yeah, we haven't gone through and done it. 5 minutes. So this is a plot here. Yeah, so this is a frequency dependent value, but we haven't done a whole lot of work seeing it spectroscopically. But as a rough measure, it's large. So yeah. It's Q equals 0, yeah. So it's an optical experiment, yeah. So it's all zero momentum, basically. It's a good question, yeah. So I don't. Yeah. Yeah. So I think there's ample room here for a reasonably model independent assessments of these kinds of objects. Yeah. Yeah. Where am I looking? Yeah. So I don't know. So when you look, so let me talk about this right here. So this is a plot, temperature versus doping. That's the TC dome. Plotted out of the board here is this, again, the scale of the nonlinearity, right? And so terahertz range nonlinearity should be enhanced where non-parabolicity is large. And so in a non-interacting system. And so the question is, where is this coming from? Is it like a band structure effect, a non-parabolicity, or is it coming from interactions? And I think so. A place where the non-parabolicity should be largest is near the Lifshitz transition, which is about 0.2 in lanthanum strontium copper oxide. And so it doesn't seem to be particularly enhanced there. I mean, it seems to be, to me, a property of the whole normal state. And so I think it has to do with interactions. And so a point that was made in this paper here is that in general, you would think in strange metals, you expect that nonlinearities are enhanced by a factor of basically EF over KT. And so my feeling is that's what's going on. It's a consequence of basically linear in T imaginary self-energies. It's more enhanced on the overdope side, yeah. I mean, this is a rough measure of the scale of the nonlinearity. You know, and how does that all correspond, that of the observed nonlinearity? So it's not a measure of chi3 exactly. This is a measure of like our experimental signal here. So I wouldn't say that it means, you know, the intrinsic physics is, and so there's a complicated interplay of how much light is absorbed at some particular frequency, how much nonlinear light is made from a nonlinear process. So yeah, so we haven't done that. Yeah. Yeah. So one other, maybe I'll just go on with this. There was one or two other points I wanted to make, but I want to get to the, what's that? not talking about Kagome metals, yeah. So, so this is plots. So these were kind of rough experiments of the nonlinearity on the previous page. So here we start to apply back to this idea of 2D terahertz, right? And so again, that's what data looks like when we take it in the time domain. And these are the Fourier transforms in various forms. This signal is also not particularly frequency dependent. And so it is easier for us very often to do these experiments and to do the analysis in the time domain. And so that's what's plotted. Apologies, here on this plot. So we've worked on a lot of samples which span the underdoped all the way up to the overdoped. And so these are plots where we pump the sample with a terahertz pulse and then come in at some later time and probe the sample and look at the response. And so red is warm and blue is cold, and these curves can be fit. And what I plot on the next page here is, on the left side is the momentum relaxation rate. Literally, it's just the width of this Drude peak that we get from linear response. In red, I'm plotting this other response, the relaxation rate, which is this energy relaxation rate. And they're plotted on different scales, right? Note the different scale between the two sides here, right? It's approximately a factor of 20 between the left and the right sides here. So in all cases, the energy relaxation rate is an increasing function of temperature. So that's important. Remember what the old Phil Allen result was that if I was in the elastic regime for phonon scattering, the energy relaxation rate would be a decreasing function of temperature. And in all cases, it is the energy relaxation rate is much, much smaller than the momentum relaxation rate. So we can take a few things from this. One, in a regime where the momentum decay rate is, if you will, Planckian, the energy decay rate is not Planckian. We find that the relative rates of the energy and momentum relaxation, they indicate that most scattering that leads to resistivity doesn't carry away energy from the electronic system, right? So it doesn't mean that it's elastic scattering, but it could be electron-electron scattering, if you will. But electron-electron scattering doesn't take away energy from the electronic system, right? It just reorganizes energy within the electronic system. The fact that that gamma E is an increasing function, the energy relaxation rate is an increasing function of temperature, shows that there's no large coupling to some kind of bath at temperatures above their Bloch-Gruneisen temperature. In other words, we're below the effective scale that the electrons, the bath that the electrons are coupling to, that they're losing energy to. So you're at temperatures which are small compared to the effective scale of the bath. And the takeaway point from both of these is that, and this is something that people, of course, believe for many years, but I think we've really shown it for the first time, is that linear T resistivity in the cuprates cannot come from phonons. So I think this is experimental demonstration of that fact. There's a number of open questions here, and one of the things that I'm curious about, what else have we ruled out, if you will? Have we ruled out things like coupling to other collective modes? And so, of course, electrons coupling to phonons is just one thing, but there's, of course, a large literature of how electrons can couple to other collective degrees of freedom. Those other degrees of freedom could be collective modes which are themselves electronic in origin. And I think there's an interesting question or not, whether or not those other possible collective degrees of freedom can themselves be a bath to take away energy from the electronic system. And so I think here there's some analogous story that has played out in the context of things like many body localization. Can the electrons be a bath for themselves? Yeah, so that's, I think, all I wanted to say to that. And how much time do I have? I'm done. I have 5 minutes for questions and that's it. Yeah, okay. I'll just take 30 seconds to say that we worked on a number of different metals, and if you're interested in these topics, these papers are available in the archive. We worked a lot on strontium, doped strontium titanate, and there's an interesting story here as well. One of the funny things about strontium titanate, we might call it the mystery of T-squared resistivity. And so strontium titanate shows T-squared resistivity at low temperature, at low dopings, where the dopings are so small that the Fermi surface is so small that essentially the electron-electron interactions cannot be Umklapp. But yet it shows T-squared resistivity anyway. And so this is of some debate about what the origin to this is. And one of the possibilities is that the source of the T-squared resistivity is not coming from electron-electron interactions, but it's coming from some kind of, if you will, weird phonons because of the unusual lattice properties of strontium titanate. And I think what we show in our results, and I'll just say it here in words, is that we rule out this scenario as well, because we show that we are in a regime where, again, the energy relaxation rate is an increasing function of temperature, and this scattering, which is T squared, is much, much larger than that. So you can't, if you will, postulate some kind of weird acoustic phonons that are giving you some funny power law that's giving you a T squared, that's leading to T squared resistivity. So that's something that we rule out as well. And I'll just finish with that, and I'm happy to take questions.
Yeah, it's very interesting that your non-linearity extends across the whole superconducting dome. But
yeah.
The obvious question is, I'm sure with Ivan, he's able to extend beyond the superconducting dome with his films, or whether that non-linearity persists into the putative Fermi liquid regime.
Yeah, so it doesn't appear to. We don't have many films out there. Oh, where is it? There.
Yeah.
But that's the highest dope that we went to there, where TC was 0. We don't really, Ivan doesn't really have a good measure of what's the doping out beyond when we can kind of, based on conventional wisdom, go from TC to a doping, but out to at dopings where TC goes to 0, we don't know what the doping is anymore.
But you can see if the resistivity recovers T squared, and then the question is,
yeah.
Does the
and so what it looks like, and this goes along with the idea that there's a component that the nonlinearity is basically related to linear and T resistivity. Because from your work, we think that we lose any contribution of linear and T at that point. And then the nonlinearity seems to be going away. Yeah, so that seems to tie together. That's a point we make in the paper.
What about undoped cuprates, energy relaxation?
So yeah, that would be interesting, but they're insulators. And so there's no, here we're thinking about the low energy degrees of freedom. Basically, how does the Fermi surface? You can do it, but there's not, you can couple to magnetic degrees of freedom, possibly with the terahertz pulse. But there's no Fermi surface to look for energy relaxation.
The thermal conductivity is very unusual.
Yeah, in terms of the, you mean in terms of like the thermal Hall effect, for instance? Yeah, yeah. That could be interesting. Yeah, I haven't thought about it.
Yeah, you say have this large chi3. Did you measure the temperature dependence of chi3?
So it's right there.
Whatever you call X.
Yeah, so I mean, this again gives you kind of a rough scale for how things fall off. To take this values here and turn it into a chi3, we would have to do a little bit more work that we just didn't do in this paper.
Because the theory paper you mentioned there has the theory paper you've mentioned there that has a particular temperature dependence for this quantity. So
yeah, we probably should do that analysis.
Yeah. So maybe I didn't get it properly. So the common idea was in the overdoped regime, actually, the correlation effect is much less. And the Fermi surface at the overdoped regime measured has a very good agreement with even the band structure Fermi surface. So I'm a little confused when you were saying in the overdoped regime also, you really see this kind of nonlinearity. So where it is coming from, I mean, is it?
So this is an experimental result. So yeah, so that's the way it is. So that's a good question. Where does it come from? I mean, I think that again, there's a few possibilities, and just to put them roughly, one is large non-parabolic. If we're thinking within the theory of conventional metals, large non-parabolicity in the band structure, which would be enhanced at 0.2-ish, because that's where there's a Lifshitz transition where the Fermi surface basically goes from being closed around pi to being closed around gamma. And that should have the largest non-parabolicity. but it doesn't seem particularly peaked around 0.2.
That's what you were pointing
Yeah.
out. That's
And
why
then
it's
the
more-
other possibility is for large, basically inelastic scattering or energy dependent scattering would be a better way of saying it.
Mhm.
And yeah, overload equiprates are perhaps less interacting
Yeah.
than other ones, but they're not weakly interacting metals. And so
Yeah.
I think that's the essential thing. They're still strong, you know, by any, we've done experiments, and in fact, you can see here, we did experiments here on niobium nitride and gold films. And so niobium nitride shows large nonlinearity in the superconducting state, and then it's just flat in the normal state. That's niobium nitride, flat, and that's gold, right? So, you know, that's a conventional Fermi liquid gold, and it just shows no nonlinearity that we can measure at all. So overdope cuprates are yeah, less interacting, but still, they're still strongly interacting by some standard.
Yes, over there, yes.
Mhm.
So, you know, do I have to worry about that here? You know, can one tune, you know, this sort of bottleneck about how quickly the photon will break?
Yeah, it's a good question. So we've done work, I didn't present it, we did work, actually the first material that we spent a lot of time working on was strontium ruthenate. And in strontium, it's not very apparent in the cuprate data, but in strontium ruthenate, there's a really long time signal that just so it looks very similar to this, but the signal doesn't completely go back to where it was on the scale of 10 or 20 picoseconds. It seemed to still persist for the longest amount of time that we had. And we understood, you know, what we argued in that paper was that this was a very long time scale that was associated with diffusion of heat out of the film altogether. They're thin films, and so I think that they're reasonably well coupled to the environment. But whether or not, you know, is this something that's very important for, you know, the kinds of statements we're making here? I think it's probably not. You know, I think that, yeah, the phonons do go out of their equilibrium distribution. Is that a major thing to take into account in a quantitative description of the data? I think probably no. But yeah. Phonons?
Yeah.
The optical phonons?
Yeah.
I actually don't know, but we're not, I mean, the optical phonons are not going to play a strong role here because we're at much lower energies below all of them. So it's the acoustic phonons, which are we're coupling to primarily, I would guess. Right? So there's a whole host of optical phonon modes, which kind of start in the tens of millieV range, but are probably peaked around 20, 30, 40 millieV.
Okay, I can see there are still many questions, but I think we should move on to the next talk, and we can continue with more questions here or over tea after the second talk.